going to talk about an important inequality more on the theory side of things. We're not going to use this a lot in practice, but it's a good thing to know, especially if you're working with vectors. And that is the Cauchy Schwarz inequality. And what the Cauchy Schwarz inequality says is that the absolute value of A dot B is less than or equal to the norm of A times the norm of B. Now we know this is true in 2 or 3 dimensions. In 2 or 3 dimensions, we know that A dot B equals the norm of A times the norm of B times cosine of theta. And we know that from the law of cosines. So there's no doubt about this fact. So this implies the Cauchy Schwarz inequality because cosine of theta is between -1 and 1. So we're good there. So again, like if you took the absolute value of both of these things, you'd still be in good shape. But that is not the whole story, because in 4 or more dimensions, we don't really have the law of cosines because we kind of have to make up what angles mean. In fact, we use the dot product to define angles. So we no longer get to just assume the Cauchy Schwarz inequality because of the law of cosines. The proof for it is a bit technical, but I'm going to draw you a picture that kind of does the job, and I'll fill in some details. But more importantly, we'll do an example. So let's say I have 2 vectors, A and B. So here's B, and here's A. And I don't actually care about A too much, but what I do care about is the projection of so we'll call this vector. We'll draw it in green. This is the projection of B onto A. And you'll notice I'm drawing a picture in 2 dimensions. This is to give you the intuition, but the math works no matter how many dimensions, as long as you use the same projection formula as you do in 2 or 3 dimensions. So if this is B and this is the projection of of B onto A, then this is going to be B minus the projection of A onto B. And we have to figure out which way we want to point the arrow to make that work. So I think that is the way that we'll want to draw that arrow. And by the Pythagorean theorem, we know that the absolute value, the norm of the projection of A onto B plus the projection, I'll write Pythagorean theorem to show what we're doing, plus the norm of the projection of B minus projection of A onto B. If you square these and add those together, then you're going to get the norm of the third side. There is a caveat here that you will see in your homework, which is first, you need to show that this is only necessarily true if the projection of A onto B dot B minus, I'm going to erase that, B minus the projection of A onto B equals 0. This ends up being true if you do the math. So we're allowed to use this Pythagorean theorem. And once we use the Pythagorean theorem, what do we get? Well, the norm of the projection of A onto B squared, that's going to be A dot B over the norm of A. That's just the norm of the projection. And we're squaring those things. Plus, I'm not going to do any simplification here because I actually won't need to, which is a wonderful thing. Equals B squared, the norm of B squared. And then I'm going to multiply this whole thing by a squared. And what we get is that a dot b squared plus, I'm just going to write some positive number, because what it is it's the norm of b minus the projection of b onto a squared times the norm of a. I'll actually, non-negative is more correct, because technically this length could be 0. It's not in the picture I drew, but it could be, and I'll leave you to think about when that would be the case. So we have a dot b squared plus some non-negative equals the norm of a squared times the norm of b squared. Since everything's positive, first of all, what that lets us say is that a dot b squared is less than or equal to a squared b squared, those norms. I've been forgetting arrows like a maniac here. And last but not least, you can square root both of those because it's all positives. That won't affect the inequality in any way. And you will end up with a dot b is less than or equal to the norm of a times the norm of b. So really what the proof boils down to is show that you can use the Pythagorean theorem by showing that this dot product equals 0, and then just do a little bit of algebra. So why is the Cauchy Schwarz inequality nice? Well, we'll get to that in the next video, but let's just do a quick example of demonstrating that it's true. So up here, we're going to verify the Cauchy Schwarz we'll stick with 4-dimensional vectors. How about 5, 5, 7, -1, and we'll do 0, 3, 0, 4. So let's verify Cauchy Schwarz. How would we do that? Well, let's see what the absolute value of the dot product is. The absolute value of a dot b is going to be the absolute value of 5 times 0 is 0, plus 15, plus 0, minus 4. That's going to be 11. What about the norm of a? Well, the norm of a is going to be the square root of 5 squared is 25, 5 squared again is 25, 7 squared is 49, and 1 squared is 1. Hey, guess what? Those add up to 100, so it's a perfect square. Wow, it's like I planned it. So that equals 10. What about the norm of b? That's going to equal 3 squared plus 4 squared, which hopefully you recognize, a little Pythagorean triple there. That's going to end up being 5. So the norm of a times the norm of b ends up being 50. So what the Cauchy Schwarz inequality is telling us is that 11 is indeed less than 50. It turns out to be the case for these two vectors. So there's the Cauchy Schwarz inequality. We're going to see why it's important in the next video. So there you go.